Hello, my name is Richard Bell, and I'm with the Kalamazoo Astronomical Society. And today, I'm going to talk to you about galaxies, island universes. Before we begin talking about galaxies themselves, let's talk about, of course, what is a galaxy? So a galaxy is a large system, and they come in a variety of sizes. They can range anywhere between 10,000 to several 100,000 light years in diameter, where of course 1 light year is the distance light travels in 1 year. So if a galaxy is 100,000 light years in diameter, it takes a beam of light 100,000 years to travel from one side to the other. And they can contain gas and dust, millions to hundreds of billions of stars. And in the case of one galaxy, they can contain you. And these galaxies are isolated from their neighbors by hundreds of thousands or millions of light years. But as we'll see, galaxies can be pretty big. So if they're just several 100,000 light years apart, they can actually be pretty close. So even though galaxies are enormous and they're all over the sky, we had to discover them first. So for most of human history, the Milky Way was just this diffuse band of light arcing across the sky. No one knew what its true nature was. From a very dark site, far away from the city, with no moon, you just see this kind of ghostly gray arc across the sky. You can't really tell its true nature. So people made up stories about it. In Greek mythology, the Milky Way got its name because it was the breast milk of the goddess Juno as she nursed the young Hercules. And because some of the milk spurted into the sky and not young Hercules' mouth, he missed out on his chance for immortality. Instead, he just became very strong. But as a result, we got the Milky Way. So that's why we call it the Milky Way. It is the breast milk of the goddess Juno. At least that's what the ancient Greeks thought. So here we see the Milky Way. This is somewhat of a realistic view of what the Milky Way should look like, created with a program called Stellarium, which can be downloaded for free. And of course, today, a lot of people can't see the Milky Way. So it's said that 1/3 of all people around the world cannot see the Milky Way because of man-made light, light pollution. And this includes 80% of all Americans. So if you get a chance to take a vacation far away from the city during new moon, try to enjoy the Milky Way. It's your birthright. But again, for most of human history, we did not know what this diffuse band of light is. We got the answer when Galileo Galilei first turned his telescope toward the night sky. So Galileo did not invent the telescope. That's kind of a common misconception, but he did sort of reinvent it. He found like a technical guide of how to build a telescope, but he said, I can build a better one. So he did build a telescope more suitable for astronomical applications. And eventually he turned it toward the night sky. And what he saw was so amazing, he rushed a small book into print called The Starry Messenger. And in that, he reported 3 major discoveries. Number 1 was the moon was not perfect. Number 2 was that there were 4 moons that revolved around Jupiter when all heavenly motion was thought to be centered upon the Earth, so that was a big deal. But the third one, which is not really appreciated in his time, was that the Milky Way is composed of stars. And you can see a quote from Galileo here, where he says the galaxy is nothing other than a mass of luminous stars gathered together. And by the way, that term galaxy, it's just a term that means milk-like. So we always referred to the Milky Way as the galaxy, this milk-like thing that arcs across the sky. But Galileo showed with his very small early telescope that the Milky Way is composed of stars, too far away and too close together to be seen individually. And you can prove this yourself. If you do go out to a dark site, during new moon, bring out some binoculars or a telescope. No matter how small, it's probably better than what Galileo used. And you can see that the Milky Way is in fact composed of stars. Now, in Galileo's day, they were really more concerned with the structure of the solar system. Was Earth the center of the solar system, or was the sun the center of the solar system? So, spoiler alert, it was the sun. The sun is the center of the solar system. And that's why the other two observations in the Starry Messenger, with the moon, and especially the Galilean moons of Jupiter, those were much more important than his discovery of the Milky Way at the time. So that would have to wait a couple of centuries to really realize just how important that was. But then we jump ahead in time a bit, and we see Thomas Wright here. Thomas Wright was an English astronomer, mathematician, instrument maker, architect, and garden designer. People were quite multifaceted back in those days. And so he was the first to describe the shape of the Milky Way in his publication, An Original Theory or New Hypothesis of the Universe, that he published in 1750. And so you can see his quote here where he speculated that the faint nebulae people were just beginning to discover through telescopes were really distant galaxies. And most of them, or many of them, were. So you can see his quote here where he says, "The many cloudy spots, just perceivable by us, as far without our starry regions, in which thou visibly luminous spaces, no one star or particular constituent body can possibly be distinguished. Those in all likelihood may be external creation bordering upon the known one, too remote for even our telescopes to reach." So again, what he was saying is many of these fuzzy objects that we can see in the night sky with telescopes were probably galaxies like the Milky Way, but that would require more evidence. But then this gentleman turned toward the Milky Way itself. So here we see William Herschel, one of the most famous astronomers in all of history. He was actually born in Germany and became a musician, but eventually in 1756, he migrated to England and he pursued, again, music as a career. But he also had an interest in mathematics because there's a lot in common between music and mathematics. And this interest in mathematics led him to astronomy, because at the time, mathematics was a branch of astronomy because they were considered both abstract subjects and not really related to physics. But now, of course, astronomy is a branch of physics. And so one day, while observing, as part of his hobby, he discovered a planet, Uranus. And this was done on March 13th, 1781. And this was a huge deal because Mercury, Venus, Mars, Jupiter, and Saturn had been known about since ancient times. So nobody had ever discovered a planet before, but Herschel was the first to do so. And this made him very famous. And he was able to pursue astronomy full time. So eventually his sister Caroline immigrated to England and worked as his assistant. And one day he decided to try to create a map of the Milky Way. So while William Herschel made the observations, his sister Caroline took all the notes. So they attempted to gauge the true shape of the Milky Way star system by counting stars in 683 different directions in the sky. And here's the result of the research, this kind of irregular, kind of disc shaped, because they always knew the Milky Way was kind of flat because we can see this kind of, arc across the sky. It doesn't encompass, this glow doesn't encompass the entire sky. So this is what the Milky Way should look like from far above. And they really did think the sun was the center of the Milky Way, but this is really just a result of the people making the map. So later on, we'll see a current view of what we think the Milky Way looks like from far above, and it doesn't resemble anything that Herschel saw. So this was a pretty first crude attempt to make a map of the Milky Way. And speaking of his sister Caroline Herschel, at first she was just his assistant, but eventually she began using and making telescopes of her own. and she discovered more comets than anyone alive at her time. And she was so successful, she became the first paid female professional astronomer. So she became a very good astronomer in her own right. Then we jump ahead a bit to this gentleman here, William Parsons, the third Earl of Ross. So he was known as Lord Ross in Ireland. And so Lord Ross here was educated at Trinity College, Dublin, and Magdalen College in Oxford, and he graduated first class with honors in mathematics in 1822, and he inherited an earldom and a large estate in Ireland when his father died in 1841. So he used his tremendous wealth to create this telescope, which became known as the Leviathan of Parsonstown. So this is a very large Newtonian reflector. So what we have here is this very long tube with a primary mirror in the back, but it's not a mirror in the modern sense, as I'll explain here shortly. But the mirror here was 72 inches in diameter. And so what happens is the light from objects in the sky comes straight into the telescope, reflects off this curved mirror, and up to a flat secondary mirror, which is at a 45-degree angle, and then the light, greatly amplified, comes into this eyepiece here where you can see this gentleman looking through. So just imagine using this giant telescope in Ireland on a dark, clear night. It'd be a little scary to be up on this scaffolding here. I'd be afraid of falling over. I would imagine they had some kind of harness system to protect people from just such scenarios, but I really don't know for certain. And so you can see this telescope is housed in a very different facility. It's not like the modern observatories we have today with big domes and stuff like that. Unfortunately, this telescope here could only move up and down in altitude. So you could not turn it in azimuth, to different directions in the sky. So you had to wait for an object to rise in the east, briefly move through the field of view of the telescope, and then it would eventually set in the west here. And the only time you could view the object was when it was moving through your field of view, and that was it. And they used, pulleys and levers to move the telescope up and down. So very, very different from today's standards. And I mentioned way at the bottom of the telescope there is a 72-inch mirror. But today's mirrors are made of glass, of stuff like Pyrex and quartz, and they're coated with a layer of aluminum or silver, and they're highly reflective. Today's mirrors are like 97, 98% reflective. But this is made of a metal called speculum, which is an alloy of tin and copper, and at most had half the reflectivity of a modern day telescope. So even though this was a 72-inch telescope, it probably had the kind of light gathering ability of a 36-inch telescope, which is still pretty good. And so this telescope was by far the largest of its day, and showed Lord Ross objects in the sky like no one ever saw before him. And so here's one of the sketches by Lord Ross on the left. And any amateur astronomer would know what this is. This is M51, the Whirlpool Galaxy. But back then, they didn't know there were other galaxies yet, so it didn't quite get a name yet. So because some of these nebulae, these kind of cloudy objects in space, had a spiral structure, these became known as spiral nebulae. And astronomers really had a gut feeling that this was in fact another galaxy, but they needed to gather more evidence. But jumping ahead here a bit, M51, shown here in an image on the right, was the very first galaxy to be classified as a spiral galaxy thanks to the work of Lord Ross. And so you can see the great spiral galaxy here. This is actually another galaxy passing near M51. And you can see the spiral arms in the image here on the right as well. So then we jump ahead to the early 20th century, and we'll talk about the work of Henrietta Swan Leavitt. She began work in 1893 at Harvard College Observatory as one of the women human computers brought in by a gentleman named Edward Charles Pickering to measure and catalog the brightness of stars in the observatory's photographic plate collection. So what would happen, of course, is the men would take the pictures with the telescopes, which for some reason women weren't allowed to do back then. Don't ask me why. But the women were the computers, which was a term they used back then to say, this is the person that does the measurements and does routine calculations. But she made a pretty amazing discovery. One day, she was analyzing pictures of what we now call the Small Magellanic Cloud. And the Small Magellanic Cloud is actually a satellite galaxy to the Milky Way. It contains its own stars and clouds, gas and dust. And she discovered 2,400 variable stars in the Small Magellanic Cloud. And some of those variable stars had a light curve that matched a star called Delta Cephi. And so these were now known to be Cepheid variable stars. And she noticed with these Cepheid variable stars that the brightest had the longest periods. So in other words, the way they change in brightness was linked to their true brightness. So if we know how bright they appear in the sky, their apparent magnitude, and we can figure out their absolute magnitude, their true brightness, we can use them to measure distances. And so this relationship between the brightness and the period became known as the period luminosity relationship. And she was the first to discover this, but she couldn't calibrate the method. That was left to somebody else. But first, let's take a look at the Small Magellanic Cloud. So again, this is a galaxy which orbits the Milky Way. So the moon is a satellite because it orbits Earth. So because the Small Magellanic Cloud orbits the Milky Way, or at least we think it does, it's a satellite galaxy. So it's a smaller galaxy that orbits our bigger galaxy, the Milky Way. And again, in this galaxy, she discovered 2,400 variable stars. And again, the curve of those stars matched the curve of Delta Cephi. So this graph here shows the light curve of Delta Cephi. So here we see the star at its brightest. So this is one star and it changes in brightness. It goes from its faintest to its brightest, and then it gets faint again and gets bright again. So the period of pulsation, because these are stars that pulsate because their atmosphere swells and shrinks, and as the atmosphere swells up, it gets brighter, and as the atmosphere shrinks back down, it gets dimmer again. So here's where the atmosphere is all puffed up and it's very bright, and it gets dimmer again and gets brighter again. So the period is from bright to faint to bright. And so Delta Cephi has a period of about 5.4 days. Some can last much longer, but again, their period, the time they take to go from bright to faint to bright, is directly related to their true brightness. And so they can be used as standard candles to measure distances much farther than we could with other means. So, but again, somebody had to calibrate the method, and that was left to this gentleman here named Harlow Shapley. Now, Harlow Shapley did not set out to become an astronomer. He actually wanted to become a journalist. So he tried to enroll in the journalism department at the University of Missouri, but he was told they hadn't built it yet. So instead of going home, he decided to pick whatever came first in his course catalog. Now, the first thing listed was archaeology, and he didn't know what that was. So he picked the second thing, which was, of course, astronomy. And he was like, well, I know what that is. I'll do that. And that's how he became an astronomer, because it was the second thing listed in his course catalog. And he would go on to become one of the greatest astronomers of the first half of the 20th century. So he went on to study eclipsing binary stars, where two stars orbit each other, but one appears to block the other from Earth, so an eclipse. And he studied those while he was a graduate student at Princeton. But then once he graduated, he got a job at Mount Wilson Observatory in California in 1914 and used the 60-inch telescope to find out what made Cepheid variable stars tick. Why did they change in brightness? And he was the first to figure it out, that their atmospheres swell and shrink. So here is the globular cluster. So what Harlow Shapley did is he actually measured the distances to globular clusters. He found Cepheid variable stars in globular clusters. Not only could he measure the distance to the globular clusters, but mapping their positions across the sky helped him kind of map out the size of the Milky Way. But his initial size was 3 times larger than we now know. We now know the Milky Way is about 100,000 light years across, but he thought it was about 300,000 light years across, because he did calibrate the Cepheids, but not totally properly. You know, he didn't know there are 2 different types of Cepheids, and those he used were the fainter type, and so he overestimated the size of the galaxy. So this globular cluster shown here is called M13, and it's in the constellation Hercules, so it's also known as the Hercules cluster. It's about 26,000 light years away, so we see it as it looked about 26,000 years ago, and it's about 145 light years across, so definitely not big enough to be considered a galaxy. And it contains about 300,000 stars, and we know it's about 11.65 billion years old. Now, these globular clusters, as mentioned, are outside the Milky Way. They're not really in the galaxy, but they orbit around it. And M13, shown here, takes about 500 million years to complete one orbit about the galactic center. And its orbit carries it out as far as 800,000 light years. So it can get pretty far from the Milky Way. And so you see the globular cluster here, and we can see another galaxy up here. This is called NGC 6207. I know it kind of has a boring number like that, but it's really hard to name all these objects because there are so many of them. So Harlow Shapley calibrated the Cepheid variable stars, or at least he kind of got us in the right direction, and he was able to kind of give us a rough idea how big the Milky Way was. But he really didn't prove that the spiral nebulae that Lord Rosse observed were in fact other galaxies. The absolute proof that there were other galaxies in the universe was ultimately left to this guy here, Edwin Hubble. And if you're thinking, does he have anything to do with the Hubble Space Telescope? The answer is yes. The Hubble Space Telescope was named in honor of Edwin Hubble. So, like Harlow Shapley, Edwin Hubble was born in Missouri in 1889, and he moved to Chicago, though, in 1898. So he actually spent most of his life in Chicago. He actually went to the University of Chicago and studied astronomy and math, but he went to Oxford on a Rhodes Scholarship and studied law. And for a time, he did practice law in Kentucky, but he discovered he hated it. He said he would rather be a first-rate astronomer than a second-rate lawyer. And so he did some odd jobs for a time. He was a Spanish teacher, a phys ed teacher, and a basketball coach. But eventually, he did go back to the University of Chicago and got his PhD in astronomy. But then World War I happened, so he did fight in World War I. But once he returned home, he became a staff astronomer at Mount Wilson Observatory and worked with Harlow Shapley. And around this time, they had a much bigger telescope. Remember, Harlow Shapley used a 60-inch telescope, but Edwin Hubble got to use this new 100-inch John D. Hooker telescope, named after, of course, John D. Hooker, who was a prominent local businessman and gave them all the money to build the telescope. So you can't quite see it here, of course, but down here somewhere is a mirror 100 inches across. So that's even bigger than the Leviathan of Parsonstown in Ireland, which was long under disrepair by this time because Lord Rosse, passed away. And so this showed the sky like no other telescope did before. So now we go to an actual image by Hubble, not by the Hubble Space Telescope, but by Hubble himself, the man. And so this is an image of what was called the Andromeda Nebula. And you can see there are actual notes by Edwin Hubble on here. He has the letter N everywhere, in here, and N crossed out here. The N stands for nova. So a nova is where you have a star called a white dwarf that pulls in matter, gas from a companion. And every so often, this gas gets ignited and it appears to get really bright for a short time. So that's what a nova is. And you can see, this is probably a nova here, this is a nova here, but you can see he crossed out the letter N here and realized that this was a variable star. And this star is actually right here as seen by the Hubble Space Telescope. And you can see it getting brighter. When it's brighter, that's when the atmosphere is all puffed up. And when it gets dimmer, that's when the atmosphere shrinks back down. And you can see its position in a more modern image of the Andromeda Galaxy as shown here. So Hubble realized that this was a Cepheid variable star, and he used it to measure the distance to the Andromeda Nebula and realized that, of course, it was the Andromeda Galaxy. Hubble's initial estimate was 900,000 light years, but today we know the Andromeda Galaxy is actually 2.5 million light years away. So you can see they didn't quite yet fully calibrate the Cepheid variable measuring distance method. So they had to work on that a little bit. But still, at even 900,000 light years, that was clearly beyond the Milky Way. So this was definitely another galaxy. So Hubble proved that many of these spiral nebulae were in fact other galaxies. So there really were other objects like the Milky Way in the universe. So now we have a universe of galaxies. And Hubble's first task when you first discover these objects is to classify them. Because if you classify them, maybe you see certain evolutionary traits and you can see how they evolve or change over time. And that's what Hubble thought he found here with his Hubble's galaxy classification scheme, or as most people call it, the Hubble tuning fork diagram, because it looks like a tuning fork. So he thought that elliptical galaxies, which are kind of round or, elliptical, he thought as they rotated, they would flatten out to become spiral galaxies. But now we know that's not the case. So, but still, this is the basic way we classify galaxies today. So on the handle of the tuning fork, we have elliptical galaxies. And so you can see after the E, which of course stands for elliptical, there's a number. Now the number comes from measurements of the galaxy put into this little equation right here. So we measure the diameter and the thickness of the galaxy. So let's say the diameter and the thickness of the galaxy are equal. A is equal to B. So if A and B are the same thing, this is 0. So if you're an E0 galaxy, that means you're spherical. You're really not elliptical at all, but you're spherical. But we still call it an elliptical galaxy, even though it's round. But if A is larger than B, then the number gets, bigger and bigger, the bigger A gets. So E0 is very round, but E7 is, it's shaped more like a football than it is what you might think of a galaxy. So here is an elliptical galaxy. This is one called M60, which is about 56.7 million light years away in the constellation Virgo. And it also contains a 4.5 billion solar mass black hole at its center. So I really like this image because we see the really big difference between elliptical galaxies and spiral galaxies. But of course, let's talk about the elliptical here. You can see, of course, they're very round or elliptical in shape. And they tend to have a more yellowish color because elliptical galaxies contain very old stars, kind of yellow stars like the sun or even redder. So they tend to have a kind of a yellowish color to them. And there are no bits of gas and dust in this galaxy. So there's really no star formation going on in elliptical galaxies. So what probably happened billions of years ago is this galaxy made all of its stars at once, and that was it. It used up all of its gas and dust. So all the stars in elliptical galaxies are very old. And they're what we call metal poor stars. Now, let me explain what that means. So, you know, the periodic table where you have hydrogen and helium. Now, hydrogen and helium are, of course, gases, which were made mostly in the Big Bang. You know, all the hydrogen was made in the Big Bang, and most of the helium in the universe was made in the Big Bang. But everything else was made in stars. So every other element besides hydrogen and helium, at least to an astronomer, is called a metal. So when we say the stars in elliptical galaxies are metal poor, that means the stars are almost nothing but hydrogen and helium. And that tells us these stars are very old, several billion years old, you know, maybe upwards of 11, 12 billion years old. So they're round, they're kind of yellow, and the stars are very old and metal poor. Now, elliptical galaxies are just the opposite. You can see they're blue because they contain lots of really young blue stars, because blue stars don't last very long. They tend to blow up after maybe just a few million years. But there's lots of them being made. So there is star formation in spiral galaxies, as we'll see later. And so their disks are very blue. And you can see there's lots of gas and dust to help make new stars. But we'll talk more about spiral galaxies here later. Now, elliptical galaxies come in the most extreme range of sizes. They can be super giant elliptical galaxies like M60, the galaxy we just saw, or they can be much smaller, like this galaxy shown here. Now, technically, this is a spheroidal galaxy, but they're very similar to dwarf elliptical galaxies. They're all really almost the same thing. They're very old and metal poor, but they're a lot smaller. This galaxy here, and yes, this is it, this is the galaxy, is only, only 820,000 light years away. So that's close enough that it's probably a distant satellite of the Milky Way. So this galaxy most likely orbits our galaxy. And again, it probably only contains a few million stars, and there's no star formation and no gas and dust. So these types of galaxies, specifically dwarf elliptical galaxies, are considered the most common type of galaxy in the universe, because even the nearby ones are really hard to see. This one wasn't discovered until like the 1950s. And by the way, this galaxy here is really close to the star Regulus, which is at the heart of Leo the Lion, the constellation. So once we get past the elliptical galaxies, we get to these oddities here called SO galaxies. SO galaxies are also known as lenticular galaxies. So this is the lenticular galaxy PGC 10922. It is 200 million light years away in the constellation Octans, which is in the southern hemisphere. Now, lenticular galaxies are structured very much like spiral galaxies. They have a disk, they have a central bulge, but the disk does not break up into spiral arms. And in a way, they're like elliptical galaxies too, because you can see it's yellow. So remember, if it's kind of yellowish, that means it's made up of very old stars. So in lenticular galaxies, they're flat like spiral galaxies, but they contain old stars like elliptical galaxies. And you can see there's very little star formation. There is some gas and dust here toward the center of the galaxy. So there probably is some star formation here. In fact, you can see maybe it's a little on the blue side, but overall, they're like elliptical galaxies in that they have old stars and there's very little star formation in them. And these are kind of a rare type of galaxy. So again, these are SO or lenticular galaxies. But then we get on to the most popular, the spiral galaxies, because they look so beautiful in images. On the top here, we have the regular spiral arms. So from a central bulge, we have spiral arms emanating outward. So if you're an SA galaxy, then you're a spiral galaxy with tightly wound arms. If you're an SC galaxy, then you're a spiral galaxy with very loose and open arms. So SBs are intermediate. They're not really tight. They're not really loose. They're, kind of in the middle. So here is an SA galaxy. This is a very popular one to amateur astronomers. This is called M81, or Bode's galaxy. It's 12 million light years away in the constellation Ursa Major, which contains the Big Dipper. And again, it has a mixture of both young and old stars. There's very old stars in the central bulge of the galaxy. You can't really see it bulge here too well, but you can if it's closer to edge on. But in this case, we don't see it edge on. But here they're very yellow, so it contains very old stars like an elliptical galaxy. And there's very little star formation in the centers of these galaxies. There is some, but not very much. But you can see the disks are resolved into spiral arms. And because the spiral arms are very tightly wound, it's an SA spiral galaxy. And you can see again it's blue because again it contains young stars, and you see all these little pink knots. These are nebulae, or basically the places that make new stars. So spiral galaxies have lots of star formation in the disk, amongst the spiral arms. Now here is an SC galaxy because the arms are fairly loose and open. This is NGC 6946, which is known as the fireworks galaxy, because on average, you get one supernova, one star that blows up every 100 years. But in the past 100 years or so, this one has had at least half a dozen stars blow up. So you can see why we call it the fireworks galaxy. So this one is viewed nearly face on, so we can see the spiral pattern a lot better. So it has the central bulge with very old stars and the spiral arms in the disk, which are composed of very young stars that range from everything from blue stars to red stars, every temperature of stars. And this one is pretty small compared to our galaxy. It's only about 40,000 light years in diameter, and it's about 25.2 million light years away, right on the border of the constellations Cepheus and Cygnus. So it's kind of in two constellations. And now on the bottom here, we have the barred spiral galaxies, which means from the central bulge, the center of the galaxy, you have a bar of stars and gas and dust. And from the ends of the bar, you have spiral arms emanating outward. So if you're an SBA galaxy, you guessed it, you're a barred spiral with tightly wound arms. If you're an SBC galaxy, you're a barred spiral with very loose and open arms. So again, an SBB is a moderate or kind of intermediate barred spiral galaxy. Now here's a beautiful barred spiral galaxy. This is NGC 1300, which is 61 million light years away in the constellation Eridanus the River, very close to the constellation Orion the Hunter. This one's about 110,000 light years across, so pretty comparable to the Milky Way. And again, you can see the central bulge is very yellow, telling us the stars are very old, like those in elliptical galaxies. But from the central bulge, you see this beautiful bar of stars and gas and dust. And from the ends of the bar, you see spiral arms. And because they're tightly wound, this is an SBA barred spiral galaxy. And again, in the disk, we see lots of star formation, like in a regular spiral galaxy. Now here is an SBC galaxy, but this is not an actual image of a galaxy. It's an artistic picture because this is the Milky Way. This is what our galaxy probably looks like from far above. But our galaxy is a barred spiral galaxy of the SBC type. So it has a bar with very loose and open arms. So, yep, this is probably what our galaxy looks like from far above, but we'll talk more about that here shortly. Now, one other type I want to mention is not shown on the Hubble tuning fork because they have odd or irregular shapes. And those are irregular galaxies. Now, for quite some time, this galaxy was considered an irregular galaxy because it didn't really seem to have a definite shape. But look at it really closely. It is one of the galaxies we just talked about. Can you see it? We'll give you a second. If you're thinking, it kind of looks like a barred spiral galaxy, you're right. You can see the central bulge. You can see kind of a spiral arm here, kind of a short stubby one, and an even shorter stubby one here. So either this galaxy here, the Large Magellanic Cloud, was a barred spiral galaxy, but has been pulled apart by the Milky Way, or because of the Milky Way pulling on it, it's evolving into a barred spiral galaxy. But earlier, I showed you the Small Magellanic Cloud, and that is truly an irregular galaxy. Now, again, the Small Magellanic Cloud and the Large Magellanic Cloud shown here are galaxies. They just happen to orbit the Milky Way. And this one is about 160,000 light years away, so a little closer to us than the Small Magellanic Cloud, and it's about 14,000 light years in diameter. Unfortunately, you can only see the Small and Large Magellanic Clouds from the southern hemisphere, so we can't see them from Michigan, unfortunately. And you can see this galaxy has lots of nebulae. This one here is called the Tarantula Nebula. And this is one of the largest known emission nebulae in the universe. Emission nebulae are also known as stellar nurseries because these are the places where stars are currently forming. This thing's about 1,000 light years across, which is roughly over five times the size of the more famous Orion Nebula. In fact, if this were the same distance as the Orion Nebula in the sword of the constellation Orion the Hunter, it would fill half the sky. So it's huge, especially given the size of the galaxy that it's in. Now, I mentioned that galaxies can be tens of thousands or millions of light years apart. Now, if they're only a couple million or a few 100,000 light years apart, that's really close together given how big galaxies can be. So it should come no surprise that galaxies are not isolated. They are not really island universes. They are grouped into clusters of galaxies. So yes, we do have star clusters, but we also have galaxy clusters. And they come in two basic types. You have poor galaxy clusters, which might contain 10 to 100 galaxies, or you have rich galaxy clusters, which can contain thousands of galaxies. Now, we live in a poor galaxy cluster called the local group of galaxies. At present, it contains 55 known galaxies, and of the bright galaxies, 14 are dwarf ellipticals, 3 are spiral, or 4 if you really count the Large Magellanic Cloud, and 4 are irregular. And you can see the Milky Way at the center here, not because we're really at the center, but we're the ones making the map, you know, so we put ourselves at the center. And earlier, I showed you the Leo 1 dwarf galaxy. There it is there. And aside from the Milky Way, you can see 2 other pretty good sized galaxies. Again, the Andromeda galaxy and M33, which we'll meet later. So again, we live in the Milky Way, so we only have real pictures of the Milky Way from the inside. And so here's a pretty amazing picture, you know, of the Milky Way. Sometimes people ask me, well, where's the sun? Well, it's behind the camera because we're the ones taking the picture from the solar system. But this is what the Milky Way looks like from the inside. And so you can see the disk of our galaxy, and crossing in front of this, the disk crosses in front of the center of the galaxy, which is right here. And nearby, you can see the large and the small Magellanic Clouds. So again, these galaxies orbit our galaxy. At least we're pretty sure they do. We're not 100% sure about that. But what would the Milky Way look like when seen from far above? I showed you earlier, but here's another artistic view of what our galaxy would look like from far above. And we'll turn on the map here and we can see the position of the sun. So the sun is located about 2/3 of the way from the galactic center, roughly 28,000 light years. So the center of our galaxy is 28,000 light years away. And yes, our galaxy does contain a supermassive black hole called Sagittarius A star, and it's about 4 million times the mass of the sun. But remember, it's pretty far away, so it's not going to pull us in. In fact, stars like the sun orbit the center of the galaxy. It takes the sun about 240 million years to complete one orbit about the galactic center. And so you can see many of the spiral arms are labeled. We have the really large Scutum Centaurus arm, but we live in a little branch arm called either the Orion Spur or the Orion Cygnus Spur or the Orion Cygnus arm. It has many different names. It doesn't really have an official name, but I'll call it the Orion Cygnus arm. So that's where the sun is. That's where we live in the Milky Way galaxy. And as mentioned, there are other spiral galaxies in the local group. The Milky Way is not the largest. That title goes to the Andromeda galaxy that we met earlier. So as mentioned, the Andromeda galaxy is 2.5 million light years away. And it does contain several satellite galaxies, 2 of which can be seen here. Both are dwarf ellipticals. So here we have M32 and this is M110. These galaxies both orbit the Andromeda galaxy. And this is the largest and most massive galaxy in the local group. The bright portion of the Andromeda galaxy, roughly from here to here, is about 130,000 light years across. But if you include the fainter outer parts of the galaxy, shown in this amazing picture here, it's about 220,000 light years across. Now, our galaxy probably contains between 200 and 400 billion stars. The Andromeda galaxy probably contains upwards of 1 trillion stars. Yes, trillion with a T. And this galaxy also contains 100 million solar mass black hole, which means it's 100 million times more massive than the sun. So a lot more massive than the supermassive black hole in our galaxy. Now, the third great spiral in the local group is M33, the Triangulum galaxy. We call it that because it's in the constellation Triangulum. And this one isn't quite edge-on. The Andromeda galaxy is pretty close to edge-on, but not perfectly edge-on. This one's tilted toward us by about 54 degrees. And this is the smallest of the three. It's only about 60,000 light years in diameter and contains about 40 billion stars, which is a lot, but nowhere near the amount that the Milky Way and the Andromeda galaxy contain. And this could be a satellite galaxy of M31, the Andromeda galaxy, but we're not really certain about that. And as far as we know, this galaxy, even though it's pretty good size, does not contain a supermassive black hole at its center. But it does contain NGC 604, which is one of the largest known emission nebulae, about 1,500 light years across. It's even bigger than the Tarantula Nebula in the Large Magellanic Cloud. So those are the 3 great spiral galaxies in the local group. Now, there are other galaxy clusters near us. The nearest rich galaxy cluster, with lots of galaxies, is called the Virgo cluster. The Virgo cluster contains about 2,000 galaxies in all. And the very center of the Virgo cluster is the galaxy M87. This is one of the largest known galaxies in the observable universe. It's several 100,000 light years across, and it contains maybe somewhere around 2 to 3 trillion stars. It's huge. So finally, let's take a little tour of the universe. We're going to begin with the sun here, about 2/3 of the way from the center of the Milky Way, and move outward. So now we see the entire Milky Way galaxy with the large and small Magellanic Clouds, and we see other galaxies in the local group. Now here we see the Andromeda Galaxy and the Triangulum Galaxy, and we just see how feeble the local group of galaxies is. And now you can see why we call it space, because out here it gets quite empty. Now here we see another poor galaxy cluster. This is probably the M81 group, which is the nearest cluster to us, but it only contains about 30 galaxies, so that's why it's a poor cluster. And now we pass through a rich galaxy cluster, very much like the Virgo cluster of galaxies. So you can see it contains several thousand galaxies, but you haven't seen anything yet. Now, we used to think that the local group and the Virgo cluster were part of the Virgo supercluster. But we now know the Virgo supercluster is just a lobe in the much larger KAS supercluster of galaxies. And now each one of these knots is a supercluster of galaxies containing tens of thousands of galaxies. And superclusters are grouped into long filaments and walls of superclusters. We now know there are at least 200 billion galaxies in the universe, but that number could be well over 2 trillion galaxies in all. And this is what we call the large-scale structure of the universe, where galaxies are in clusters, clusters are grouped into superclusters, and superclusters, shown here, are connected again in walls and filaments of galaxy clusters. The supercluster that we are part of is known as the Pisces-Cetus supercluster complex. So finally, let me show you your place in the universe, or you can also call this your complete galactic address. So currently you are at a certain address. Perhaps you're at home. So you put in your home address here, and you live in a certain city and state. So for me, Kalamazoo, Michigan, and that is no doubt located within the United States. The United States is located in the Western Hemisphere, or of the North American continent, which is located in the Western Hemisphere of the planet Earth. The planet Earth is the third planet from the sun in the solar system. The solar system is part of the Orion Cygnus spiral arm, which is part of the Milky Way galaxy. The Milky Way galaxy is a member of the local group of galaxies. The local group of galaxies is part of the Virgo supercluster lobe. And as we now know, the Virgo supercluster lobe, as I call it, is part of the Laniakea supercluster of galaxies. And the Laniakea supercluster of galaxies is part of the Pisces-Cetus supercluster complex. That's the galaxy filament that we live in. Remember, the filament is basically a string of superclusters of galaxies. And the Pisces-Cetus supercluster complex is part of the universe. So there's your place in the universe. And now we know about that and the other galaxies in the universe. So thanks for listening.